Thank you all for staying for the last talk. I will try to not take up the full 30 minutes. So we're going to talk about automating entity relationship diagram construction on Iceberg data lakes. And my name is Wes Madrigal, co-founder and CEO of a little company called Curve. We spun out of a research institute just down the road from here about a year and a half ago called SRI, where I incubated the company, formerly Stanford Research Institute, no longer associated with the university. What else? My background is mainly ML engineering and a little bit of data science. So I used to run a small consulting practice where I would do data science and ML ops engineering, which was really where the company Curve was born, because I would consistently onboard 3 to 5 customers at a time and have to learn their data lakes in parallel. So it became a huge inefficiency for our little consulting practice to parallelize onboarding customers and learning all their data lakes. So this is actually just a diagram I had GPT generate for me. I've read a bunch of diagrams about where, data scientists and ML ops engineers are spending their time, but most of them only focus on when we're working on a data task. So I kind of wanted to get GPT to tell me, even including one-on-ones and conferences like these, how much time in our year, in our day goes to data prep, data understanding, and business understanding. I think that's a more holistic picture than say the 80-20. So it came back with, about 30%. I know it's a little hard to read, but 30% on data prep, 8.5% on data understanding, and 5.7% on business understanding. So still a pretty large slice of our time going to this, even in 2025. I tried to prompt it to say, read the most up-to-date research, even with all the Gen AI advancements, and try to give me your assessment. So that's where it landed. So this, really turns into, we got about 400,000 data analysts and scientists, according to the Bureau of Labor Statistics in North America, around 100,000 on average. And so ultimately, this problem costs about $20 billion a year in the US, right? This is where a lot of our time is going as professionals in data. This data understanding, data prep, business understanding. Okay, so a little boring, I know, those graphs, but they're relevant to contextualize. So my question is, why does it still take so long in 2025? Given an Iceberg lake, these modern stacks, given a data bricks catalog, why is it taking so long to understand the data and prep it for analytics and AI? Well, so most of these were designed for schema on read, right? That's a feature, not a bug. So most of the relational metadata about the interconnectedness of all of your files and tables is just not there because we didn't have to document it up front. We threw a bunch of tables in the data lakes and then accumulated this tech debt over the years, right? So data warehouses are just a thin layer on top of these files, these Iceberg files or Parquet files, and they have no relational metadata. So many organizations have sort of centralized here, but they have no ERD, no semantic layer. It's getting solved, but it's not solved yet. And I just wanted to fact check myself. That was my opinion. So, GPT responded, number one reason why it costs so much to understand and prep data in 2025, schema on read. No enforced schema makes understanding data slow, complex relationships. Gemini was similar. Second point was lack of standardized metadata and cataloging. So again, kind of confirming this. And really my whole career, it's kind of been this, advancement of AI and techniques. And I come from sort of the tabular world, not revision and NLP, which has been revolutionized. But in the tabular world, you still have to do all this data integration to do model.fit, right? The prospect of AutoML never came true because it required we have a singular table with a Y variable that you can call .fit on. But the reality is most of our data lakes are hundreds of tables sprawling, and we have to integrate them together to train a single model, right? And so the ideal goal would be parameterize a data lake, an entire lake, say nothing else but the target you want, and then call .fit. So how would we accomplish that? So we would need to automate the extraction of the following at minimum: primary keys, foreign keys, date keys, cardinality. These are the basic metadata constructs of doing group bys, doing joins, filtering and point in time correctness, Obviously, you have to know how much to deduplicate. If you've got a one-to-many relationship, so you need cardinality. All of these are lacking out of the box in most modern lakes if you don't have a team actively on top of it, which most companies don't. Could be a possible Iceberg spec addition just to add a little foreign keys. Key value here, I'm not a committer, but if anyone in the room is, I think this would be a great idea. So Curve uses graphs as a metadata layer to represent these entity relationship diagrams. We represent the tables as nodes, the relationships as edges. Graphs are just really good for this, right? Like you have the whole graph library stack, network X, things like that. So not reinventing the wheel. And just to make it clear, we're using graph as knowledge representation, not information storage, right? So not transforming your data and storing it in a graph structure like Neo4j, it's just for the metadata representation layer. And so this is what, a data lake might look like in a graph form. You have this interconnected structure, you see things, and you can drill in. So here's an example, 5 Iceberg table data lake, and it's just got some flat files, some flat Iceberg files. We can infer the relationships between these, and you get this nice little graph structure. So the high-level algorithm here is, number one, extract the primary keys. So we run some operations like uniqueness checks, ordinal, semantic likelihoods of the headers, et cetera, and pick a primary key per table. Then you can loop through every column compared with every single other column in all the tables, which is a polynomial time problem. So you can't explore all combination possibilities, but you can get to, okay, what are the types similar candidates? And then you can start using semantic similarity of the headers, and then you can do some data profiling. And ultimately, we've developed algorithms over the last few years coming out of the research lab that combine, LLM, general purpose reasoning with data profiling and get an algorithm that can actually go deeper than just headers. Because as you'll see here shortly, headers just don't get you the whole way there. So, okay, so this is what it might look like after you've got, primary keys generated on an Iceberg table. You got a node for the tables, and then, over on this side of the image, you've got, the table name, the columns, and then there's an assigned primary key and date key. Foreign keys, again, so we're looping through every column compared with every other column, doing semantic header checks, doing data profiling. Sometimes even if it's a really questionable joinability, we might actually have to push a computational join down to the warehouse and say, okay, join this left to right and right to left, and what's the overlap rate bidirectionally? That's really expensive, so we can't do that until the very end, right? If you've got 100 or 1,000 tables at petabyte scale, you can't join every table, but we do that near the end to prune out a lot of the spurious connections. And so you've got this little metadata graph, right, with which you can navigate your Iceberg or Databricks or whatever catalog in a way that's a little more rich than your just flat list of tables that tells you nothing more than the name. So cardinality is obviously, just inferable based on the row count, right? If you've got a table that's a child of another table and the relationship, you can very easily see if it's one-to-many. Date keys, a lot of tables could have multiple date keys, and this is really important for doing analytics and AI. You don't want to use like the date it was inserted or created in the lake. You want to use the date the event was emitted. So getting that right is really important, especially from a metadata layer when you're going to streamline downstream analytics and AI on top of it. And just a little bit larger of a data set. So we pumped this Microsoft worldwide importers data as Iceberg tables in, and I think there's like 50 tables, and just, ran our algorithms against it. This is a subgraph. It's a little squeezed. Should have cleaned that up, but it's essentially a subgraph with 32 relationships. And so you can kind of see how these, just enumerated list of your files, like it doesn't give you a ton if you're not intimately familiar with the data. And, thinking as a former consultant, I would encounter new data lakes on the regular, right? Knowing nothing. And so Curve was sort of the idea of like, okay, encounter a new data lake, and within one day, I know everything, right? Maybe even more than the most trained employees in the company. Okay, so question you might all have, does it actually work with, semantically meaningless headers and things like that, right? And this is really where the LLMs break, is some of these schemas in, data lakes are going to have very meaningless headers. I don't know if you can read that much, but it's like these underscores and MD5 hashes and table names. And there's actually a common column that's like SDC source key ID in literally almost every table, but it references different parent dimensions and parent relationships. So you never know what it's pointing to, right? So you end up having to get into this data profiling based extraction to infer when they're connected. And our algorithms are able to do this, right? So we ran it on this schema, and we were able to pull out, actually, even with no semantic usability in the headers based on the data profiling implementation, and without having to run a full join, if they're likely connected, right? And so that's a little bit deeper. And one of the reasons we ended up having to go deeper than just say, ask Gemini or GPT. That's just zoomed in a little bit so you can see some of those keys and kind of how used they are. Okay, so maybe asking, okay, great, Wes, you can build a relationship graph that serves me once and then it never serves me again in a recurring basis. The idea behind Curve is also, really you can represent your data in a graph, but then that allows you to loop over all of your tables in a graph way, whether it's breadth first or depth first, and do roll-ups to arbitrary dimensions. So coming kind of from the data science and analytics side of things, everything in the tabular world is oriented around particular dimensions in your company, a user, a product, a quarter, et cetera. And so your data lake is like this huge, multi-hierarchical set of your business, right? With different time dimensions and different intervals. And ultimately, for any given problem, you want to view the data through the lens of a particular dimension. Dimension could be customer, could be product, et cetera, right? So this becomes a graph problem very naturally, where your parent node in a hierarchical relationship is that dimension, and you're doing a depth first roll up to that dimension, right? So that's essentially an interop between, you've got this metadata layer, and now you can push looping over it using basic SQL primitives like aggregation to roll things up to a particular dimension. So that's what we've done. And so once you combine this metadata layer with the compute, you get this really interesting automated data integration interface. So without kind of going into all the details of this example, there's an open source benchmark called the Relational Deep Learning Benchmark. It's out of Stanford. They have like 7 or 8 databases and a bunch of different predicted problems on each one. And you can benchmark, kind of different relational machine learning against those, right? But one of the noteworthy things is the data is stored in its native form in like many tables, right? So this particular schema has 7 tables. They don't pre-merge the data for you with nice X, Y, dependent and independent variables. You have to do it all yourself. And a lot of the papers that have approached this problem takes around 20 hours to prep these 7 tables just for a problem. So with Curve, knowing nothing about it, we can do it in like 15 minutes. So those 7 tables, 8, we ended up pulling out this schema graph on those, and immediately, without sort of knowing anything, we were able to get this relationship graph. For the problem that we were looking at, it was a predictive problem around the user dimension. So we can use the graph to sort of orient all those tables around that user and see what its closest foreign relationships are. Again, this is like, if you think about looking at just a list of files, it's not clear immediately which tables are 2 or 3 joins away from the dimension that you're interested in this case, the user, because they may be sitting right on top of one another in the list, but there's actually no distance geometry in there, being on top of one another. In a graph, you can see, okay, these are 3 joins away, 2 joins away, right? And you may want to constrain your data integration to local neighborhoods of data to start with versus aggregating your entire, 1,000 table data lake. Okay, so, how would we go about kind of creating compute graphs with these schema graphs? Specify a parent node, so the dimension to which you're going to integrate and aggregate, the depth limit, which would be the maximum number of joins you're going to allow the integration to run. The compute period would be, how long in history you're going to consider, and a few more things like label and target. But in summary, you can essentially parameterize top-level parameters here across arbitrarily large compute data integration graphs constrained by a depth, right? So in this case, we were using depth 2. And so this is essentially going to say, all right, for all the tables that are depth 2 away from user, roll them up and don't consider anything farther back than a couple of years, and use this date. And since it knows all the date keys in each table, it knows which date to do the filter on, it knows which keys to join on, it knows which keys to group by, it knows which ones need to be deduplicated because they're a one-to-many relationship. It knows all that. That's all simple metadata on a per table basis that just gets pushed into the data integration process. So how does this actually work? It just basically does a depth first traversal based on cardinality to the bottom, right? Think like events or whatever your high frequency data capture is, going to the bottom, doing filters, point in time aggregation, and repeat until you get to the top, right? And so with our customers, we've got compute graphs running at depth 6, 7, on terabyte scale that are running these. So it really doesn't matter how deep you go. It just is a question of how much you want to constrain. Do you want 30,000 columns at the end of it? So for this relational deep learning problem, and this is too much to kind of go through in detail, but you could replicate this very easily on your laptop. This is all open. But if you run this against this relational deep learning data set and you run a compute graph, again, knowing very little, just saying, hey, I want to roll this whole data set up to my user level. I want to predict this thing. It'll create this flattened data set for you that you can throw into an AutoML engine. Now, it's not meant to be production grade Tecton AI feature store. It's meant to allow you to loop over your data lake and find which problems hold promise, potentially, based on aggregating data and orienting your data around that problem. Because this historically has taken weeks to months, right? Even a first draft prototype of a churn model or an LTV model in most companies still takes weeks to months, right? So the idea is, given the space of ideas that the analysts and data scientists want to explore, allow them to, in effect, loop over problems with the click of a few buttons and get signal as to which ones hold promise. That's really the value prop. So this whole notebook is open. You can use it in Google Colab. And skip that. Yeah, so the main benefits we've seen, is just a lot of these companies just don't have any kind of relationship documentation or semantic views or ERDs on their new data lake that they invested a bunch of money in. So that works as, centralizing the knowledge. We do automated feature engineering integrations, but that's really not I would say that's not like our bread and butter. Everything that's running in those computational graphs is completely customizable. Don't have time to go into it, but you can customize every single piece, right? So if you want to customize a filter, at depth 3 at node 50, you can do that and let the automation handle the rest. You can do that. Really benefits for just even finding query optimization, so shortest path through your data lake between, table A and table B. And we've started to hear recently, again, we're a pretty new company, but we've started to get some pretty quantifiable impacts on some of our customers in terms of their throughput. And we've seen graphs like the one shown here in terms of time, they're spending preparing a particular data set, spanning multiple tables for analytics and AI with and without us. And it's just a huge delta. So this is just a visualization of us scaling up one of our customers, one of their schema graphs, one of the associated compute graphs that they're running. I think the schema graph is like 70 tables for that schema, and the compute graph is maybe 20. the whole paradigm is compute push down. We don't even run our own servers. Everything deployed into customer VPCs on their premises. Definitely interesting from an intellectual property thing, but we deploy everything in and then connect up to whatever the compute layer is, push compute down. So this is actually, in this particular graph, I think it's a Redshift graph. So it's pushing everything down to Redshift with kind of a live connection. So yeah, that's it. Thank you so much. And that QR takes you to the demo where you can actually just run everything that you saw there yourself if you don't, if you may question how all this stuff works. So, yeah, okay. Thank you so much.
Think at the beginning about your course of percentage of effort for training. Are those spaces for tax rates or just standard days stuff? Come on. 60%. What kind of data is that?
Yeah, so I actually ripped the left one from, I think it was Anaconda's study like a couple of years ago. And then the pie graph, I just had Gemini and GPT summarize all the research papers that they had read and then try to build me an actual comprehensive one. Because again, all the studies say like, oh yeah, 80% of the time on data prep and data discovery when you're working on that. So like, how is it relative to your one-on-ones and your, attendance at Iceberg Summit? That was what I was trying to get at.
Can I ask you something? So
Yeah.
this was great, right? So
Thank you.
how you started with building this was based on your small consulting company experience. So today, how are you positioning your customers? What are you telling them that I can use? Your problem was you had one person trying to do like 5 projects at once, for example, right? 5.
Yeah, or even 3 trying to do 5.
Yeah, right. So how have you solved that problem today?
Yeah, so had I had Curve rolling back the clock 2.5 years and I was still onboarding new customers, it would have taken me a couple days to do what took me 60, sometimes 90. Because a lot of it would come down to like, just getting a good understanding of their lake, which they themselves may not have had, right? They themselves may not have had documentation, so therefore it was Zoom calls, Slack, a bunch of loading data into, Jupyter notebooks. The sort of how it works. It's very manual and laborious. So I think 90 is pretty on the liberal side, but being conservative, let's just say 30 to 60 days, we can automate that completely. So you onboard a new customer and you don't know everything, but you know a lot more than you otherwise would have by extracting out all the relationships. You may know more than even internal employees who think they know a lot. Then that takes you to the next step. Well, if you're a data professional, you're probably actually doing something with the data, querying it, interrogating it, integrating it. In our case, most of the time doing data integration to build a model. So kind of overlaying this automated graph-based data integration layer, that's probably the bigger speed up, right? Because that piece is where sort of the magic happens and you're pulling the signal out of the noise of the data lake and building a model and creating value for the end customer, top of the line revenue creation, right? And so we've just been showing, not telling with our customers, right? And we've actually done some of it for them. And we've said, hey, you have a team of, mid-market, 60 to 100 or a couple $100 million in revenue companies. And it's like, hey, you have a data science team. Here's how many models they're building for you. Here's how many data sets that your analysts are doing in this quarter. We'll show you that we can do 10x that in, like half the time, right? And so that's what we do. So I would have loved having this as a consultant, and I may go back to consulting with it, but for now we're trying to build a product company. So, yeah. Yeah, it was the worst part of consulting. It's automating that away. So, cool. Thank you all.